Hello everyone, I am Chandrahas Misra from ABES Engineering College, Ghaziabad. In this lecture, I am going to discuss spanning tree. So we will see what is spanning tree, what is minimum spanning tree, what are the algorithms to find minimum spanning tree, and we'll see applications. So let us consider a situation. Here we have a central office, and these are the some offices, and we want to connect these office to the central office. So for connection, we need a network cable. So this is the simple approach to connect the central office with other offices. Like we can directly use cable from central office to a particular office to connect this. It is very simple approach. But here, what is the problem? We need extra cables, or we can say uh, very large cable to connect these offices. So how can we minimize this? We can use simple approach uh, like this. Here we connect central office to this office, and after that, what we'll do, we'll just connect nearest offices from this office. So we need not to use again one cable from central office to this office, or central office to other offices. So if we'll see here, it will take less number of cables in comparison to the previous one. Okay. So this is the basic application of basic need of the uh, spanning tree. This intelligent approach minimize the total cost or total length of the cable for wiring. So how can we use in the form of graph? We'll see here. Suppose we have a graph. Let us take simple graph. This is a graph. So here we have three nodes, and this graph is connected like this. We want to find out the spanning tree for this. So in this graph, we can see here we have three edges uh, in between these vertices. So is there any other way to connect this graph? Yes, we can connect like this. We have AC and B. This is also possible. So we can take only two edges to connect this. Another way is like we can take A, B, and C. Like this, we can connect. Another way is like here we have A, B, and C. So what we have done in this, we have used AC and BC edges to connect this. In this one, we have used AC, AB and BC edges to connect this. In this one, we can use AB and AC to connect this. So like this, we have three different ways to connect the edges. Basically, the approach is we want to connect all the vertices of the graph with the minimum number of edges. Okay, so this is called spanning tree. Now, if we have suppose a graph with four vertices like this, and we have multiple edges connected to this. Suppose this is the complete graph. This is complete graph with four vertices. So here we can see we have six edges, but how can we connect these vertices with the minimum number of edges? So let us take an example for this. Suppose the vertices are A, B, C, and D. So if we connect like this, A to B, then B to C, we have one edge, and then C to T, we have another edge. Okay, so we can see here we have connected all the edges. So this is a connected with only three edges. What is the another way? We can also connect like this. We have one is from A to D, then from A to B we can have, and then we can take from B to C. So this is also another way to connect this. What is another way to connect this? We can take A to D, then we can connect A to B, and then D to C like this. This is also possible way to connect. So basically in all these cases we can see we are only using three edges, only three edges to connect the vertices of the graph. So this three number of three edges is the minimum, and these are the spanning trees. Spanning trees. So basically, a spanning tree is a subgraph. We can see the subgraph of a graph in which there are minimum number of edges in the graph, and minimum number of graphes are minimum number of edges in the graph used to connect all the vertices of the graph. So basically, this is a connected component of the graph. So if a graph is disconnected, it is not possible to create a spanning tree. So it is very important factor here. So how can we find out a spanning tree? We'll see in next. So we can see there are multiple spanning trees are possible. So how many spanning trees, if we want to calculate how many spanning trees are possible in a graph, so for this we can use a formula n to the power n minus 2, where n is the number of vertices in the graph. Okay, so let's take this example. In the this first graph, here we have three vertex. Okay, so how many spanning trees are possible? 3 to the power 3 minus 2, that is 3. So you can see here we have three spanning trees. Only these spanning trees are possible in this case. If we have a spanning tree with four vertices, in that case we can calculate 4 to the power 4 minus 2, that is 4 square, which is 16. So for this case there are 16 spanning trees possible. Okay, so what are the algorithms? We'll see what are the algorithms to find a spanning tree. So basically, there are two approaches to find. First one is the Kruskal's algorithm, and another one is the Prim's algorithm to find out the spanning tree of a graph. Basically, these two algorithms are used to find out the minimum spanning tree. Minimum spanning tree. So there is a slight difference between spanning tree and minimum spanning tree. Suppose we have a graph like this. We have a graph, and edges of the graph have some weights, or weights are assigned. Weighted graph. This is the weighted graph. So let's rename these A, B, C, and D, and we have edges like this. Suppose this is one. This is having weight uh, two. Now this is having weight. No, this is having three, and this is having two. Now this is four, and this is again two. So now we can see here all edges are having different weights, or we can say the cost associated with these edges. So there are multiple spanning tree are possible. We have seen earlier there are multiple spanning trees are possible, but we have to select the spanning tree which is having minimum cost. If we add the cost of the edges in the spanning tree, and if it is minimum, then this tree is called as minimum spanning tree. So for this, we will use Kruskal's and Prim's algorithm to find out. We'll see in next lecture. Thank you for watching this video.